Alright guys, this is a quick video for a relatively simple 2D kinematics problem, also known as projectile motion. So in this situation, we have a person just throwing a rock. I'm going to throw that rock at 15 meters per second. That's going to go, originally that's horizontal or at 0 degrees. Okay? Now we know this rock is going to follow a projectile path or a parabola right here, okay? But the most important thing that we're focusing on right now is how to set up this problem. So I'm going to come over here. I'm going to make two columns for the x and the y and all 5 kinematic variables. The first thing that you're going to do on one of these problems is you're going to take the vectors in question and split them up into their components. So the first vector we have right here is 15 meters per second at 0 degrees. So to split this up into your components, as you'll see with kind of later problems, we're going to use trig. We're going to use just trig to figure out how much is in the x and how much is in the y. But as this is a relatively simple problem and at 0 degrees, we can easily see that it is all in the x. So I'm going to say that in the x, it's 15 meters per second x hat, and none of it's in the y. It's not going up. In contrast to that, if the rock had been thrown like this, it would have some x and it would have some y. But since it is straight, it is only x and there is 0 in the y in that particular case. Okay, so I'm going to put 0 meters per second y hat. Now the next vector, which is in all of our problems of projectile motion, is the vector of acceleration. So here's gravity, it's straight down, and it's at 9.8 meters per second of magnitude. If I was to write out that vector in polar form, I'd say 9.8 meters per second squared at 270 degrees. And once again, we're going to take this vector and we're going to split it up into its components, where usually I would use trig. Like if the acceleration was down and to the left, I would get acceleration in the y and the x. As we live on a planet where acceleration is just straight down, we can do this trig kind of in our heads without doing any math whatsoever. How much of is this in the x? None of it. 0 meters per second squared x hat. Okay, and how much of it's in the y? All of it, and it's going down. So I'm going to say that's negative g. And I screwed up a second ago when putting up the 5 kinematic variables. In this chapter, we usually call that delta S, standing for space, because that leads me directly to, let's go ahead and use green. Okay, get rid of this guy right here. That leads me right into displacement. Now, the nice thing about displacement is while this is the displacement, that's its delta y, and that's its delta x. We don't usually worry about delta S as a total. We usually worry about delta X, which goes right here, and delta Y, which goes right there. And you'll notice that I said that this rock was thrown from a height of 2 meters. So this rock is going to have to go down 2 meters. So that means delta Y is negative 2 meters. The question in this particular problem is how far does the rock go along the ground? AKA it's asking for delta x. So this is what we are trying to find. Now, I made mention the other day that a 0 acceleration right here along the x means it's not, the velocity is not changing, or the x velocity is not changing. So we could take this and put it right here, but that's not really new information. All 3 of these together really just say, hey, the velocity is a constant, 15 meters per second in the x direction. So since it's constant, our equation is the constant velocity equation. And I need to know, to get delta x, I need to know these 2 things. Now I already have this one, so I need to go find time. And you'll notice right over here in the y-axis, I have 3 variables, 1, 2, 3. So I can go find time right there. So I'm going to use the equation. Displacement is equal to VIY times time plus 1/2 a delta t squared. Now, this equation is identical to the ones from previous. The two major things you have to be careful of is making sure to get that y on the velocity initial and change the displacement to delta y in this case. The reason why this is so important is because we have two of them now. We have vix and viy. And of course, in this case, we need the second one. So that's 0 and cancels out. I'm going to multiply 2 on both sides to cancel out that 1/2 over there. I'm going to divide a on both sides, and I'm going to square root both sides to get delta t. I'm going to go ahead and plug in the numbers. So I have 2 times -2 meters over -g square root. So the amount of time that it should take to hit the ground is 0.64 seconds. So that's the amount of time it should hit the ground, 64 seconds. Also, the amount of time it should be traveling in the x. So I'm going to go ahead and use that equation right over here. Plug in that this is 15 meters per second in the x, while it's falling that 0.64 seconds, and I get that it should travel 9.58 meters in the x. And that is how to do a simple projectile motion problem.